Welcome to Algorush. Today, we're going to pull back the curtain on one of the hidden, unsung heroes that keeps our entire digital world from collapsing into chaos.
Okay, so let's just dive right in. We all use databases constantly, right? Every single day. But have you ever really stopped to think about what's going on under the hood? What actually stops your bank balance from getting scrambled when you and, say, an automatic payment try to hit it at the exact same millisecond? Because that's what's happening. It is a nonstop, high-speed race. You've got reads, writes, updates, all these different operations scrambling to get at the same piece of data, all at once. And without some really strict rules of the road, the result would be, well, a total disaster. Just a catastrophic pileup of corrupted, garbled, and completely useless information. This whole challenge has a name. It's called concurrency. And really, it's all about managing these inevitable collisions, making sure that every single operation happens safely and in the right order, even when they're all trying to happen at the same time.
So these potential crashes, they really boil down into three main types of situations. First, you've got a bunch of different processes all trying to read the same data. Usually that's not a big deal. Then you've got multiple processes trying to update the same thing, which is, that's a huge problem. And finally, you get this really tricky dance where one process is trying to read data while another one is right in the middle of changing it. So if chaos is the default state, how in the world do databases enforce any kind of order? Well, they need a system. They need a crystal clear set of rules to manage who gets access to what and when.
I want you to picture this. Think of a tiny library study room. In that room, there's only one desk, and on that desk is one super important reference book. That book, that's our little piece of data. And all the people trying to use it, those are our operations. Now, to keep everyone from just ripping the pages out in a frantic mess, you're going to need a librarian to lay down the law. And that's exactly what a database has. This gatekeeper is kind of like a tiny, incredibly fast traffic cop. It stands right at the intersection where all the data requests meet, and its only job is to direct the flow and prevent those high-speed collisions. So what is this microscopic librarian, this gatekeeper for our data? Well, it's called a latch. And this little mechanism is the low-level hero that works completely behind the scenes, protecting the physical integrity of your data. Now, this is a really, really important distinction to make. A latch is not the same as what you might call a lock. A lock protects logical data, like an entire row in a table for a whole multi-step transaction. A latch is way more fundamental. It's a very, very short-term guard that protects the physical structure, the actual bits and bytes on a page in memory. And it only holds on for the tiny fraction of a second it takes to complete one single operation. So how does this little gatekeeper decide who gets in and who has to wait? Well, the logic it uses boils down to a very simple but really powerful conflict. The difference between just reading data and actually changing it. This little table here lays out the rules of the road perfectly. If you look at that top left corner, when a reader meets another reader, access is shared. They can all look at the data together, no problem. But now look at every other box. Anytime a writer is involved, whether it's with a reader or another writer, access has to be exclusive. No exceptions, only one writer at a time, period. So if we go back to our library, it's like this. The librarian is totally cool with letting a bunch of people crowd around the book and read it together. That's fine. But the second someone needs to pull out a pen and actually write in the book, the librarian shoos everyone else away. That person gets the desk all to themselves until they're done. And this shows that idea perfectly. Look on the left, you've got a whole party of readers, all sharing access, having a great time. But see that writer? It's stuck waiting in line. Now look at the right. A single writer has gotten that exclusive access, and now everybody else, readers and any other potential writers, they're all blocked, just waiting for that latch to be released. So why are we spending all this time on this tiny, lightning-fast mechanism? What's the big deal? It matters because this simple idea, shared reads, exclusive writes, is the absolute bedrock of database reliability. It's why we can trust them. See, every database you rely on makes a promise. It's a promise called ACID. That stands for atomicity, consistency, isolation, and durability. And those are the big, high-level guarantees that keep your data safe and correct. Latches are like the microscopic enforcers on the ground, the ones doing the dirty work to make sure those huge promises are actually kept, especially when things get busy. So, if we boil it all down, what do you need to remember? First, latches are the super fast guards that stop the physical bits and bytes of your data from getting corrupted in a traffic jam.
Second, by letting all the readers in at once, they give a huge boost to performance. And finally, all of this makes them an absolutely fundamental pillar for the reliability and consistency we expect from our databases.
So a latch is just one piece of this incredible puzzle, right? It's working at the lowest possible level, protecting physical memory for just microseconds at a time. Which really makes you wonder, what other hidden machinery is working at all the other levels? What about the logical locks that manage entire transactions? What other guards are standing watch